Hey everybody, it's Nate from Explorers.life, and in this video I'm going to teach you how to size wires for your DIY camper electrical setup. This video is going to focus mainly on sizing the wires for the DC side of your system. Now before we get rolling, it's worth noting that I've got nearly 20 different wiring diagrams available for totally free that already include wire sizes. So if you'd rather not do this part yourself, you can just check out those done for you options right up here. Now in this video we're going to be doing a deep dive into how to size wires, but if you stick around to the end of the video, I've made something for you that will make your life much easier. And yes, I know that there are charts out there that will help you figure this out, but I personally find that these charts make me go cross-eyed after a while, and for me, sometimes it's just easier to input numbers into a calculator. But anyway, enough of that. Let's just get started. Now there are two main reasons that it's important to have properly sized wires. The first reason is so that the wire can carry the amps that you're asking it to without heating up, and it also needs to carry those amps without having excessive voltage drop. Now each wire size has a specific amperage rating that should not be exceeded. That rule is pretty straightforward, as the values can simply be looked up, as they are always noted by the manufacturer of the wire. The voltage drop issue is a little bit more complicated though, so let's talk about it. Voltage drop is the difference between the volts available at the power source versus the volts available at the load end of the wire. Now each wire has a certain amount of resistance. The bigger the wire is, the less resistance it has. It takes voltage to push the amps through the resistance of a wire, and if the resistance costs too many volts to push the amps, there will not be enough volts at the end of the wire to run whatever device it is that you're trying to power. So to have a properly sized wire, our wire needs to meet these two conditions. They need to have enough capacity to carry the required amps, and they need to have a low enough resistance to deliver a proper voltage drop. Now a proper voltage drop is 3% for feeder circuits and 10% for branch circuits. Now we're not going to dive into that because I think it's a little over the top for this 101 level video, but when I'm making recommendations, I typically stick with 3% voltage drop, as it lowers the chance of any voltage drop issues in the future. With a 10% voltage drop, we can typically get away with using smaller wire, but since we're going to be using at most a few hundred feet rather than a few thousand feet, in my opinion, the cost-benefit ratio isn't really enough to justify risking the voltage drop issues that can possibly come around with a 10% voltage drop. But you do you. Let's put this to use and say that we have a 100 amp load, 10 foot from a 12 volt battery bank. We're going to need this formula. 12.9 is the direct current constant of a copper conductor times the amps times the total length of wires, both positive and negative, used between the batteries and the load. So you're going to want to add the total combined length of the positive and negative wires between the battery and the load. All of that divided by the percentage allowable voltage drop times the volts of our battery bank. This will give us circular mils. Now that is the unit for the number of 1 millimeter diameter circles that could fit in a cross section of wire. Now that formula we just put all those numbers into would give us the circular mils of a wire that would be required to meet the required voltage drop given the volts, the amps, and the wire length that we put into the formula. Now once we know the circular mils required, we can then cross-reference that number to what gauge of wire the circular mils would round up to. This means that to get a max of 3% voltage drop from a 100 amp load 10 feet away from the power source using 20 feet of 105 degree insulation wire being pushed by 12 volts would require 1 gauge wire. We would then double check that the amps required by the load does not exceed the maximum amps that the wire can handle. Now in our case, 1 gauge wire with 105 degrees Celsius insulation can handle a max of 247 amps, and our required load is only 100 amps, so in this case, we're good to go. Now, what happens if we have a 100 amp load positioned only 1 foot away from our 12 volt battery bank, and we still want a max of 3% voltage drop? We're going to run it through the exact same formula as earlier, and it's going to tell us to get a max of 3% voltage drop from a 100 amp load located 1 foot from a 12 volt battery bank. We're going to need a 14 gauge wire, but the max amperage capacity of a 14 gauge wire is only 39 amps, which is not going to work for our 100 amp load. So what we do now, since we know that 14 gauge wire satisfies our voltage drop requirements, we just need to look at the smallest wire that would be able to meet our 100 amp load requirements, which is 6 gauge wire, which has a maximum amp capacity of 121 amps. We made it. Now, that's a hard way to find wire sizes. Here's the easy way. I've actually developed a calculator that will do all this for you. I've left a link to the calculator in the description. Once you get to it, you may even consider adding it to your home screen so you can have on-the-fly access to it. All you have to do is put your total wire length in here, put the amps your load requires here, put the volts of your circuit here, Slide the allowable voltage drop to whatever value you like, or you can simply leave it at the 3% default and check at the top of the calculator for the wire size recommendation. Now it's worth noting that this calculator is set up to work only with wire that has 105 degrees Celsius insulation temperature rating. If you need some sources on where to purchase this type of wire, I put together an Amazon store where I've handpicked wire choices that meet this criteria, and the link is in the description. And you'll also notice that there's a recommended fuse size output for this calculator, which is also pretty cool if I do say so myself, and I'll talk about sizing fuses in the next video. But before we finish up, I want to give you a quick heads up that I've opened up options for personalized support to help you design electrical systems in your camper van or RV. I've got a private group where I answer questions in much greater detail and in a much more timely manner than I can manage on all of my public social media accounts or email. I'm currently offering the private support group and custom wiring diagrams, as well as one-on-one consulting calls. Now, if you don't need personalized support or you don't want to pay for the info, that's totally cool. I still have all kinds of free information about designing solar and electrical setups for RVs and camper vans, and you can browse all that information in the description below. So that's all there is to this video, and I hope you found it helpful. If you did, it'd truly mean the world to me if you would share it with somebody who could also benefit from it. And if you enjoyed the video, give it a thumbs up, subscribe if you want to see more videos like this one, and I will see you in the next video.